So, I'd like to continue in the tutorial vein that John started. He had the unhappy task of actually deriving the bloody equations, and now I'm going to try and give you, the purpose is to try and give you a little bit better physical intuition into their basic behavior. What I want to do is go through what I call the classics, a set of simplified model problems that I basically worked through over quite a long period of time to build intuition into how these things work. And this is work done with a large number of people. Most of them happen to be in this room or organizing this meeting. One person not here is Kian Wilson, who's been working with me recently on some of the computational issues of how you deal with these equations. So yeah, spelled McKenzie right, by the way, the little c up top. What? Nothing. I just happen to. It's an arc. That's what we really want to know about. But it's pretty. Whatever. Okay. What I want to do is, if you can stand it, spend a little bit more time on formulation, a few more PDEs, and I'm going to take what John's done and take it a little bit further into a form that I find most useful for actually working with these, which, as he said, separates these two fundamental behaviors, this incompressible flow and compressible flow, which describes the basic deformation of the solids. And I'll show you under certain approximations, you can take those two pieces apart, understand them individually, and then as you make more assumptions, those parts become more and more coupled, and by understanding the coupling between them, you can get more of these phenomena that we've been talking about, things like these shear bands, melt bands, reactive channels, and I'll talk about the simplest versions of those problems there as coupled problems. And the purpose I want to get across is that this is a coupled system of nonlinear PDEs. Small changes in your assumptions of constitutive relations or different couplings can very much change their behavior. And so if I have a little time at the end, I'll talk a little bit about work we've been doing to try and develop better computational tools for handling these kind of problems, where you need a lot of flexibility because quite often you make a small change and you need to change your solvers or the whole fundamental, what you're actually doing. But I don't know if I'll get there. Let's go back to equations. So you're all completely happy with this now. There will be a quiz at the end. You can derive that. Point is, this is not what I actually work with. I work with something much more closely to what John wrote down, but slightly different formulation, so I want to take you through it. The key insight for me back in my PhD was that there were these two basic modes of deformation. There is large-scale shear of the solid, okay, and then there's volumetric changes due to compaction or changes in porosity. And that's reflected in, where's the big bamboo stick? I like that. Okay, and this is reflected really in the solid momentum equation in the sense that the pressure, and again, we're assuming this is the fluid pressure, gradients in this dry fluid flow, but it basically is balancing three individual terms. The first term is variations due to deviatoric stress. This is the deviatoric strain rate tensor times the viscosity. Volumetric stresses, so the divergence of the solid times the bulk viscosity, and a background sort of body force, a lithostatic pressure gradient. And so I found it's rather convenient to separate, just do a linear decomposition of the pressure, okay, into three terms that basically accommodate each of these terms. So starting from right to left, I'm going to just start by saying part of the pressure is some constant background lithostatic reference pressure. So it's just some constant density gradient times the depth. And that's mainly going to balance most of this. There'll be some part that's residual, but that'll drive buoyancy, etc. The really important one for me is this one, okay, which I'm going to call the compaction pressure. And it's basically this combination of the divergence of the solid field times the bulk viscosity. Okay, that is a pressure, and in fact, this is exactly the gradient of that. Okay, and the last part, little p here, is the dynamic pressure, and that's just going to accommodate everything else that I haven't picked up yet. All right. Oh, sorry, I should also add, as John said, this is supposed to be a tutorial, so please heckle. I do best when I'm heckled anyway. So anyway, so if you assume this pressure split, okay, and just take them back into basically those equations. And I'm going to scale them now with basically the natural scaling that John introduced. Just to remind you, I'm going to scale, and this is important, I'm going to take a dimensionless quantity, the porosity, which goes between 0 and 1, and I'm going to scale it by another dimensionless quantity. But phi naught is a reference porosity. And the assumption in all of this is that that porosity is reasonably small. There's a little bit of fluid and a lot of solid. Okay? And we'll use this as a small parameter to do some simplifying approximation. In this case, I'm going to scale all my lengths by the compaction length, which is the natural length scale. All my velocities, I'm using hopefully the same notation as John's, by this separation velocity, which is basically just the background driven velocity given by gravity and the permeability, the percolation velocity. Time is just simply the time it takes to move at that speed over a compaction length. Pressures, I'm going to scale by the density difference between the solid and the liquid, gravity, and the compaction length. This is basically the pressure difference you would have for a column of melt versus solid of a height of compaction length. And that's the natural pressure scale. And I'm going to scale the shear viscosity by some reference E to naught. And we'll come back to this a little bit. I'm going to scale the bulk viscosity. There's reasons to believe this is not a bad scaling by the shear viscosity divided by this reference porosity. If the bulk viscosity looks like eta on phi, okay, that it becomes infinite as you go to 0 porosity, then that's actually the appropriate scaling. So you take all those things, mix them together, put them in, and this is the split that I use. It's a little bit different. But the reason I do this is, if you notice, so it's still a coupled system, but I think of this really as two sets of coupled problems. The first one here is basically a nearly incompressible Stokes problem. This is basically the left-hand side of this looks like a Stokes problem, okay, where the porosity is acting as a body force, a buoyancy term, okay, and this pressure here, remember this really is div V, the pressure here drives volumetric flow, okay. But you notice those are both of order phi naught, and that's going to be convenient. So I separated into so if you knew the porosity and the pressure, you could solve for the large scale solid velocity here, and it would look a lot like a Stokes problem. Okay. Then, so this is the one that you had back up in here. I'm going to split this one out, and the rest of these things is a coupled problem for the porosity, evolution of porosity, which again depends on volumetric strain, that's div V, okay, plus any change in porosity due to melting, okay. And then what you're left with is a equation for the pressure, okay, which is, it's basically this one here. We expand this, well, you had it written slightly different. So this is div V, okay. It says the divergence of the velocity is equal to the negative divergence of the fluid flux, but the fluid flux depends on the permeability, pressure gradients, including a pressure gradient due to this volumetric strain. And this is where the interesting stuff's going to come in. Okay. So as I said, capital K is permeability. Sorry, I just haven't substituted in. Questions? Yes.
In the first equation on top of the slide, why isn't there a gradient of compaction pressure in the equation?
Because I've taken it out.
Okay.
Sorry. Important point. I have defined the compaction pressure. Go back. No, it's not there. Because, well, it is if you want. There's this issue here, right? I wrote this in, I wrote this in terms, we'll get to this. I wrote this in terms of the deviatoric strain rate tensor, okay? So what I've really done is I've split this into, we'll get to it. If viscosity is constant, you can do a few more things, okay? But this was the variable viscosity case. I want to do the most general one because we'll come back to it. What I've done here is this piece here is the deviatoric stress tensor. It's not incompressible, it's just trace-free. They're not the same thing, okay? But there's an extra little piece of the divergence that is hiding in here, okay? And the divergence is related to the compaction pressure. But I've kept this here because this is really, even though this has divergence in it, this is the trace-free part. So this is just a way to split it. And I'll show you, it's more cleanly separated when the viscosity is constant. We'll get back to that. Okay, so, but the point I want to make is, the whole system here is coupled. To solve the problem, you have to solve all of them, and it couples in multiple ways. As I said before, these ones will give you V and P if you know, the solid velocity and the dynamic pressure if you know the porosity and compaction pressure. Okay. Likewise, if you solve those, the compaction pressure depends on the gradient of the dynamic pressure. So they're coupled directly through the fields.
And small pressure is
Little p, no. So this is key. Let's go back to the beginning. That's the fluid pressure. Big P is that. I've broken it up into 3 pieces. This one's just to subtract out the background lithostat. These are the 2 that are important. This one is the pressure due to volumetric change against the bulk viscosity. This one is the dynamic pressure in Stokes that would show up, which basically enforces incompressibility. It's the part that balances this piece for the most part.
Is it a tensor or is it a solid?
No, this is a linear decomposition. They're just 3 P. I can cut it up any way I want, but.
I'm not understanding things.
I'm leaving. But I haven't done anything. I've just defined things. Yes.
Is trace free.
Yes.
Right. So when you've done all this thing,
Yeah.
where is your bulk viscosity disappeared?
No, it's right there.
Further down.
Oh, no, okay, here's the magic. It's very simple. I'm going to, so when I define it this way.
Right there, next slide.
No, but I'm going to do it here. Substitute this in with that definition, right? So grad big P is grad little p, grad calligraphic P, and that, okay? So grad, with that definition, is a grad zeta div V on that side, and there's a grad zeta div V on that side, and they just cancel out. They're all in here. I just moved them around.
But then the next slide, you said that there was a distinction between.
Where? Blah, blah, blah. Here. Let me go on a little bit, and I'm going to. Yeah, okay.
We're
not going anywhere.
To understand you going on.
Very good.
I understood you at this point. Right. Epsilon dot D, you then said, was not trace free.
No, sorry. Epsilon D is trace free. Right. It's the deviatoric trace. Right. But trace free is not incompressible. The trace is 0, but div V is not 0.
Oh, that's fine.
Right.
Yes.
But n div V is that. Okay. It's all in there. It just I moved it around.
You're going too quickly.
Sorry.
You're going too quickly for me.
That's bad. Revenge. Where was I? Let's hopefully we get there. Okay. So right. Blah blah blah. Lots of things coupled. Oh yeah. Sorry. Other important coupling. So they couple directly through the fields. They also can couple through the constitutive relationships. Okay. The most important ones being the shear viscosity, the permeability, and the bulk viscosity. All of which are likely to be functions of porosity, but it can also be functions of strain rate, etc., plus other fields. So as you change your assumptions about these, you change the coupling in the problem. And then, of course, there's the thing I keep neglecting is the mass transfer, the melting rate. Okay, and again, if the functional forms of this depend only on solid velocity, pressures, or porosity, it's closed. But most likely, these things depend on things like temperature, pressure, bulk composition. And so to further close these things, you then need additional conservation equations for those things. I'm going to mainly worry about the behavior of the mechanical system, and we'll do a little simple reactive flow, coupling it to chemistry at the end. Okay. So this is already a dog's dinner. So I want to take it apart, simplify it, and break it down into its pieces, and then build it up again. So I'm going to make a couple of assumptions. The first assumption, which is a big one, is I'm going to just start by assuming that the shear viscosity eta is constant, and so dimensionally it's just 1. Okay. And I'm going to make that same Helmholtz decomposition I did in my thesis, but a little bit differently. I'm going to write the solid velocity is an incompressible part V naught. I won't write it in terms of a potential, but div V naught is 0, so an incompressible part, and a scalar potential. And I'm also going to assume, and it's important, that this piece is actually of order phi naught. The notion is in the mantle we have large-scale shear flows, and then we have small changes in porosity. You know, going from 1% to 2% may have a very big effect on the porosity, but it doesn't have that large effect on the overall flow. So I'm going to assume that there's basically an incompressible part and some perturbation due to the compressible flow. I'm going to redefine the compaction pressure slightly. This is where this little magic 4/3 comes out of. It comes out of the assumption that the viscosity is constant. And I'm going to assume this form that the bulk viscosity here looks like is of order shear viscosity divided by porosity to some m. Now, I'd have to say, from the history of this, when we started, we really were guessing at all kinds of things for this. And in the original papers, most of this was assumed to be, this was constant, potentially larger than the shear viscosity, in which case these are actually still pretty much the same, zeta star and zeta. The best handle I think we have on this at the moment is there's some periodic homogenization work by Gideon Simpson, which looked at the microscopic problem of two coupled Stokes problems and homogenized it up into effective equations. And there he shows pretty clearly if that is the microscopic physics, then the bulk viscosity should look like the shear viscosity divided by the porosity. That as the porosity goes to 0, the system is incompressible. Okay, yeah?
I mean, as we've mentioned many times, the microscopic physics includes diffusion creep, which is
No.
formulated.
I know that. What I was going to say is, for the problem he did was two coupled Stokes problems. That's the answer you get. If there's other microphysics, you're going to get different effective, but you need to do that. That's the second workshop, so which I'd really like to get to. So I'm trying to be clear about this. Yes. So this doesn't have to be true, but this is what was in there. The important part, it doesn't change the qualitative structure of the physics. What it does change very much, though, is your assumption of the length scale, the compaction length. So if you remember, the compaction length basically depends on the square root of something that looks like that. And if this is the square root of viscosity versus viscosity on porosity, if your porosity is 1%, okay, your estimates of your compaction lengths are different by a factor of 10. Okay, so we'll keep that in mind.
What sort of values of m do you envision?
0 or 1 is what people use. Okay, but 1 is the homogenization work suggests it should be 1. Okay, and that makes sense, at least in the 0 porosity limit, that the system should be incompressible, so the bulk viscosity should. Remember, this bulk viscosity is an effective property of the two-phase medium. It's not. It comes out of the homogenization of. Okay. All right. So if we do that. Then very nicely, it's the constant viscosity. This then really does become incompressible Stokes, okay? And the only coupling left here is the buoyancy due to porosity, which will drive basically convective flows, okay? And then this is the rest of this, and the extra little piece of the divergent part of the pressure goes only into this velocity. But I'm going to make one more approximation to completely decouple these two, and I'm going to assume that the porosity is small. Okay? So basically, I'm going to get rid of all the terms of order phi naught. Okay? And then we're left with a very nice little problem here, that these two things are completely independent of each other. The first one is just incompressible Stokes, driven only by boundary conditions, okay? Which says, so now they're coupled, but it's a one-way coupling. If I know, give me boundary conditions, I can solve for the shear flow and the pressure, and given those, I can then solve for the behavior of the porosity independently, the evolution of porosity and pressure. So right now I'm going to focus on this. There's an infinite number of solutions to that, but the one that was of interest to us was a simple incompressible Stokes problem as a simple model of ridge spreading. Okay. And there, it's basically corner flow. This is a modified version of it, where it says I'm basically going to take an isoviscous medium, I'm going to apply surface velocity, I'm going to pull on it u0 this side, minus u0, pull it apart. Solid's basically going to come up here, roughly corner flow. And the interesting part, though, is that because of this overall divergent flow, I'm going to generate a low in the dynamic pressure. Okay. The pressure is going to go negative here. The pressure to maintain incompressibility, the solution of this is that I'm pulling on this and the pressure drops in the corner. Now, I rescaled these equations to make them a little bit more related to this problem. So in this case, I've scaled velocities by how fast I'm pulling on it. I'm scaling the system size here by, lengths by the depth here, h, say it's 100 kilometers, okay? And then the equations, the pressure is controlled by this number here, which is a ratio of length scales. The important one here is this L. I call this the extraction length or the suction length. And it basically depends, it's the ratio of viscous stresses due to deforming this material versus the buoyant stresses of melt. Okay, and it gives you a length scale. And basically, it's the length scale over which this decrease in pressure is felt as you move away from the corner. Okay, so and the problem is that pressure, if you scale this back to make this thing large, you end up with some very, very large dynamic pressures. In fact, if it's corner flow, that's singular. I'll come to that in a second. Okay, but here's the point. Once I've separated them with this small porosity approximation, given V naught and P, I can then substitute them in here, and all I have to solve for is the porosity and the compaction pressure. But I can do one extra thing, which is a nice little approximation at this point, is I can also assume, just for laughs, that the porosity is constant and that the melting rate is 0. There's no melting, and I'm just going to assume a constant porosity. In which case, well, if the porosity is constant, that's 0, its gradient is 0, and there's no melting, well, then P is 0. And if P is 0, that's 0. And so to be consistent, the divergence of that thing has to be 0, but it is, because if I take the divergence of grad P, it's the divergence of that, but that's 0. Gone. Everything's gone. And P is 0, I ignore that one too. So, yeah, it all goes away. You knew this. This is my thesis. So, constant porosity, no melting, isoviscous. This doesn't happen for a variable viscosity system, but isoviscous system. The problem reduces to solve Stokes, and then the fluid velocity is completely determined by the solid velocity and the pressure, the dynamic pressure. Okay? And in fact, it's just a linear combination of those two things, where the proportionality, the constant is this. It's the ratio of the separation velocity, the melt velocity, okay, to the spreading rate. Okay? And it's pretty obvious what happens is, look, this thing is composed of two vector fields, the solid velocity field and a pressure gradient is basically gravity plus whatever dynamic pressure gradients. Depending on how permeable the system is, I'm either going to see this or I'm going to see that or some mixture of them. So for this value is the melt's moving 100 times faster than the solid. These are the white was the solid flow lines. This is the melt flow lines. Okay, and you get this kind of cool solution. In fact, you can do this analytically, where you extract, you basically, well, the original abstract was called Ridges Suck and So Do Arcs, which I had you approve. You didn't, anyway. There's a small issue between American English and English. But anyway, and it was a nice, simple model that explained one of the principal observations is that melt extraction at ridges is very localized to the ridge axis. Okay, and if you let L be big enough, okay, you could actually, so L is basically governs the length scale which you can sees the pressure, you can pull this out. If it's less permeable, the flow field looks more like the solid flow field. This is where this is almost a tenth. If this goes to 0, then the flow field just looks like the solid. Okay. So the only problem is, this was a nice, I like this solution, but everybody said, oh, to get this to be big enough, you need very large viscosities. And I still think that's a problem. Okay. But it comes back to, so there's some issues. What's driving this here is, what's driving this behavior is that I have this very large negative dynamic pressure in the problem, which is sucking things in. Okay. The problem is the dynamic pressure in Stokes is there to enforce the incompressibility condition. The question is, should I use that pressure as the thermodynamic pressure? If you do, I think you can end up with some very strange for this particular problem. Okay, this is sort of the extreme of it. On the other hand, though, I don't actually believe that pressure singularity is as strong as it looks, because nature, this is coming from the isoviscous assumption. Okay, in reality, if you have stresses that high, the material is going to fail. It's going to deform. It's going to change its rheology, and that's a way to remove that singularity. There's other ways to remove the singularity. So I don't think that that's going to be actually our answer, but I think it demonstrates nicely where that shear can generate pressure, pressure can affect the fluid flow and how it goes. So that's our first problem. Okay. So now what I want to do is go turn things around. Right now we were focusing on this, assuming this was constant and vanished. Okay, so now I'm going to turn it around the other way. I want to get rid of this set of equations and just focus on these, which are the fun ones.
Just if you will assume that it is compressible, you will can you handle this singularity if it was just compressible?
Not this kind of, if it was elastically compressible, but not this. The thing, it doesn't matter. This is, even if that extra p, it comes from here, it's not going to help that. What was singular is this. This is why I split the pressures. This is the pressure that's there to enforce. This is pretty still close. It's still pretty div v is pretty much zero. The small extra volumetric stuff doesn't change that. Let me explain that very well. Okay, so, but now I want to get rid of this. And so what I'm going to do is, this is true for any solution of incompressible Stokes, but I'm going to limit to the worst case is just a constant translational velocity. Okay, in which case, if that's just a constant velocity, that vanishes, and grad p vanishes, so now these are no longer coupled. You'll notice then the equations, this one is just for porosity, oh sorry, also going to get rid of melting, and now we're down to a system which depends only on porosity and compaction pressure. If the permeability is only a function of the porosity, then these two are closed. And this is just, you just pick this up as an extra correction to the velocity field, so I can get rid of that. So now what I want to do is focus on the behavior of these equations. Okay? And what they are, this was sort of basically my thesis, and the early work and all this was the surprising feature, is that this combination of equations is a nonlinear wave equation for the porosity. Okay? And so what we're going to start with here is, just to demonstrate this, I'm going to start with a simple step problem where I have a constant porosity, so in this case gravity is going that way, constant porosity going into a small porosity region. In this case it's about, the porosity is about 20% of the background here. Okay? So I have this large flux coming in, there's an obstruction in the flux, that's going to generate, there's going to be, this term is the divergence of the gravity-driven flux. It's going to drive volume changes. So instantaneously, this is actually the pressure you get. This is another notion of what the idea of the compaction length is, by the way. So given the step, you'll see that the pressure decays actually exponentially on either side of it. The length scale over which it decays is the compaction length in each side of the material. So what it says is, given a jump, okay, and it comes out of this term here, this viscous term spreads the information about this jump in the flux a little bit, it makes it non-local, it spreads it a little bit around the jump. And that actually has, whoops, no, stop, go back. I hate this, one more. Right, how do I do that? Oh, there it goes, nice. That's what happens. So you start off with a single obstruction.
What is the value for M?
And in this case, n is 3, m I've used the bulk. This is the classic McKenzie values. In the original papers we used n was 3, m is 0. We can talk a little bit about what those choices should be. It doesn't matter. As long as this is greater than 1, you'll get, we'll talk about that in a second here. Let's run that one more time for fun. Okay. So this is the behavior of this. It's not only is a nonlinear wave equation, it's a dispersive nonlinear wave equation. You start off with a single localization in the flux, and it breaks up into, in this particular case, these very long dispersive wave trains of what eventually are, if they separate out, are solitary waves. We'll talk about them in a little bit. Okay, so what's going on? Let me see if we can understand this a little bit better. So the key here is what's giving you the dispersion is this term here. Okay? And this is basically the fluid flux, the permeability times the pressure gradient times the compaction pressure gradient. Okay, so there's variations in flux due to volumetric strain of a viscous material. Okay, that's what's giving you the non-local effect, and that's what's giving rise to the waves. If you just, for fun, so what I call the zero compaction length approximation is I'm just going to pretend that this is not important. It's a dumb thing to do. But if you assume that that's not there, okay, then you'll see that this is the change in porosity in a frame, just a frame moving with the solid. This is equal to that. I can just substitute it in. Okay. And what you're left with is a simple nonlinear kinematic wave equation for the porosity. Says that the change in porosity is just advected by some velocity, I'll call it v phi here, but that velocity itself depends on the porosity. Okay? And so you can go back to Whittam anywhere you want. This thing says any place I have the flux decreasing in the direction of flow, going from high porosity to low porosity, this thing will predict shock waves. Okay? If it's going the other way, it would get rarefaction waves. Okay? But the point is, wherever, so the sort of the insight from my thesis was anywhere you generated these shocks, the flux must get small, the change in flux must become important on a scale comparable to the compaction length, because eventually it goes to no length scale. Okay? And so you can't throw away that term. Okay? This term, for a problem that generates a shock, this term will always be important. This is the singular limit problem. Okay? And what you get are dispersive waves. But one of the nice things you can do is compare those two solutions, one with the viscous dispersive term and one without. And this, I still like this figure, so I'm keeping it. So this is just basically that same problem I showed you. It started out with initial condition of porosity, and this one was chosen to exactly generate a single step shock at a given time here, in this case 2. Okay, so without viscosity, this thing just goes into this shock here, and its speed is given by Rankine-Hugoniot condition. It's easy to calculate. But what you generate is actually these dispersive wave trains which don't move at that speed. In fact, they do a lot of interesting things. Depending on the size of the jump, they always break up, in these equations, they always break up into these dispersive wave trains. Small jumps propagate quite far and everything moves forward. Everything's moving forward, I should say. The fluid is always going to the right. It's a one-directional wave equation. But information about that obstruction spreads out through these waves, and in fact, they can back up and actually disaggregate. So this was one of the big ideas, is that because these viscous dispersive problems, anything that would generate an obstruction in the flux would set these things off, and they can actually propagate and actually fill space. So it's inherently time-dependent, spatially variable problem for systems larger than the compaction length. Okay. And actually, this was revisited much more recently by Lohmann and Herfer. It's a nice paper. They actually, in my thesis, I generated all these weird little, these things, these strange behaviors that I wasn't sure if they were numerical or not. No, they're all real, actually, and they do all the analysis. It's very nice. All right. So, I should I'll seed one more thing, because we talked about the zero porosity limit. There is a question in these problems is, as this jump goes to 0, as the leading porosity goes to 0, the question is whether these things can ever propagate forward into them or not. And I think in the viscous case they can't, because the compaction length goes to 0 on that side, okay? And there's just no way to communicate from one side to the other, and I think they just back up and disaggregate. But that's not true for all problems. All right, we'll get back to that. So we'll talk a little bit about solitary waves. So in the small porosity approximation, no melting, with the assumption that permeability goes as phi to the n, bulk viscosity goes as 1 on phi to the m, you get what we'll call the solitary wave equations. Okay, or actually, they're more than that, but this is the simplification, or you can rewrite it. It's a third order, rather nasty, dispersive, non-local wave equation. But one of the obvious things you do is say, does this thing support solitary wave solutions? And so you go look for solutions that have a constant phase speed, and they do. And they exist in 1, 2, and 3 dimensions. They're hard to calculate. For certain values of n and m, they're analytic solutions. Most they're not. In higher dimensions, it's integral problem. It's rather nasty. But Gideon Simpson did a really nice job. He found a lovely spectrally accurate sync collocation method. So we can basically generate the solitary waves for these things for arbitrary n, m, and dimension. Okay, so I'll just show you what they look like. Oh, I should say, if anybody wants to, there's Python modules for computing these things, the wave profiles. They're just packaged with our software Terra Firma, which we'll talk about at the end. And I should say, anybody who wants to do computation for magma dynamics, solving these equations, this is the first benchmark you have to pass. You have to generate accurate solitary waves. It's a good test of your advection solver. Whether they're important or not in the Earth, they're really good computationally, so we make them easy to use. So this is what they look like. In one dimension, the 1D waves are, this was the 1D profile, they're all hump-shaped. In 3D, what they would really be is a sheet of porosity with isosurfaces being planar and a high porosity core that would propagate upward. The 2-dimensional waves are actually, the isosurfaces would be cylinders with the porosity profile looking like a bump. Okay. And in 3D, they're actually spherical, okay, with a high porosity core. And again, they're nonlinear waves. The bigger they are, the higher the amplitude, the faster they move. Okay. And it's been known for a long time that they're unstable. The basic analysis actually goes back to Barcelona and Rivera. We actually, quite a long time ago, computed them numerically, but this is a recent calculation. Start off with a 1D wave, let it run, and it will break up in 3D waves. Okay. So,
Can you explain what is on this picture?
what you're looking at a couple of isosurfaces and a rendering of a porosity field of a box that started off with a single one-dimensional wave. This is calculated in a frame that is moving at the wave speed. So I'm just sitting there. I couldn't find the movie. That's why I didn't throw the movie in there. But basically, I sit there. I'm tracking a single solitary wave. And what happens in time is that it goes unstable, and it pulls itself into these spheres. Okay, so in 3D, you would expect these things in a constant background with no shear, et cetera, to look like that for the viscous problem. But that's the issue. These things come because the rheology is assumed to be viscous. You can change the rheology. We talked about this a little bit. If you just change what you assume to be your constitutive relationship for the deviatoric stress tensor, you can do other things. For example, you could just assume it's elastic or viscoelastic, and I think you're going to talk about a lot about this, but I'll just give you a short version of it because it's important. For example, if this was a poroelastic problem, I could do exactly the same derivation, but instead of the compaction pressure being a bulk viscosity times the volumetric strain rate, it would be the elastic bulk modulus times the volumetric strain. Okay, that's also a pressure. That's what would fall out. But if that's the pressure, if that's divergence of the displacement field, then the divergence of the velocity field is just the time derivative of that. Okay, so I could write div v. This is what drives the change in porosity. Is now the change in time of, that should have been in compaction, of that pressure on the elastic modulus. Okay, so I'm just going to, I know what div v is in the other equation. It comes from conservation of mass. I'm just going to substitute those in here. Okay, so it says that the change in porosity with time is now the time derivative of the pressure, not the pressure, but its time derivative. Okay, and so if you integrate that up, it says the porosity is equal to its initial constant porosity plus anything you push open or compact by expansion. And the important part here is that the pressure equation goes from being an elliptic equation for the compaction pressure to a parabolic one. This is a diffusion problem. Okay. And that has a very different behavior for the propagation of the waves. So here, I'm going to compare the and this, again, this goes back, this was discussed considerably, principally Conley, Pelagikov, and papers beyond that talk about this. I'm just going to compare the poroviscous to the poroelastic problem for the same initial condition. And that's what you get. This one we saw before, that's the elastic wave. Okay. The elastic wave is not dispersive. It's actually diffusive. It moves at the speed that you would predict from the zero compaction length shock. Okay. In fact, it looks like a shock. The only thing that elasticity does, it's kind of like a Taylor shock, is that there's a small smoothing of the step due to elastic properties at the tip here. But that's it. Everything else is basically pretty much the same. So let me, okay, we can do this. Let me summarize basically compressible flow, and then I'll get on it. So what I've shown you is that the volumetric, when you split this into what I call incompressible and compressible flow, the compressible flow equations are a wave equation for porosity and pressure. The driving force for all of these waves comes from the nonlinearity of the permeability with the porosity. A region with higher permeability has a higher flux. If you have a higher flux going into a lower flux region, it's going to drive dilation of the solid. That's going to propagate. And dilation of the solid is porosity. It's going to propagate. you're going to generate overpressured waves from any initial condition that generates obstructions in the flux. Anywhere where melt can't get through, it's going to start generating these kinds of things. However, it's the rheology of the solid phase which is critical as to how the waves behave, they propagate, and their form. And so I've shown you 3 simplified versions of the rheology. If you assume there's no rheology, there's no resistance to opening, you just calculate kinematic shocks. These cannot be right. In the poroviscous case, they disperse into large sets of dispersive waves. If it's elastic, however, it actually looks much more like the shock solution with a little bit of elasticity controlling the thing. That's in 1D. In 2D, it's still diffusive, so it'll actually dissipate. If it's purely poroelastic, if I started with a finite-sized blob, it would eventually smear itself out. But that's the important part. The nonlinearity in permeability drives them. The rheology of the solid controls what they look like and how they propagate. Okay. All right. Yeah, I'm running. Yeah, I'll go. There's more I can say, but are there any questions so far? You're just like, what is this? What is this? Okay. And I'm going to get more complicated. So, I started with a problem that, when I said the solid viscosity was constant, the shear viscosity was constant, I could separate incompressible and compressible flows. Okay. But if I change that assumption and assume that the shear viscosity is not constant, then I can couple them. And this was driven, and to do this problem was driven by a set of really important experiments. Have we seen these pictures yet? I forget. No, we haven't. Okay. So these are really beautiful experiments. There were really 2 sets of them. The original ones were, let me explain what you're looking at here, were some simple shear experiments where they basically took a partially molten material. Okay, this is after the thing. So basically a homogeneous mixture of basically olivine basalt and a little bit of chromite to pin things down, and put it in a rig that simulated as well as they could simple shear of this with shear going to the right. And they found after a certain amount of strain that the melt, so ignore the vertical things, those are cracks from cooling. What you want to look at is these low angle, these black regions here. These are melt-rich bands. That the melt started out uniformly distributed, and after you sheared them, it localized into these melt-rich bands. Okay. And what was interesting is that, well, it depends on the stress, but they're at these relatively low angles to the shear plane. Okay. There's been a later set of these experiments which are done in a radial torsion rig. They're a little harder to analyze, but again, you take it doesn't matter what you do. You take one of these partially molten regions, you just shear it, and these bands form. Okay, and they form at all different stresses, and they form at all different strain rates. They're high stresses because they're experimental, but they certainly do form. And so this motivated us to say, okay, this should be actually an excellent test for these equations, because this still should be reasonably in the continuum field. It should be governed by the sort of equations we have. So can we set up a problem to understand it? So in this particular case, what we have to do, though, is we have to change, we have to worry about the shear viscosity not being constant. And in fact, what I really want to worry about is allowing the shear viscosity to be a function of porosity. Okay. So what happens there is, the key part here is when the viscosity is constant, I can take this out. When the viscosity is not constant, this first equation implies that the pressure gradient really has 2 pieces. There's the viscosity times the deviatoric strain rate. There's also a piece here that depends on the strain rate acting on gradients of the viscosity. Okay. So the viscosity is not constant. There's an extra component of the pressure, and that pressure will drive flow. That flow will drive compaction, and suddenly I've coupled shear to volumetric strain, okay, and now I have a coupled problem. So the
Theta again only function of porosity.
which one? Permeability?
Theta.
Zeta. Yeah.
No. Eta. Gradient pressure equal 2 theta.
Yeah, eta is now a function of porosity. That's the key.
Eta is a function. Oh, sorry, I didn't finish this off. Right. So this is for any variable. This is important. For any variable viscosity, you will couple incompressible and compressible flow. If the viscosity depends on porosity, then grad P will depend on gradients of porosity. Okay. So the instability The simple version of it, oops, that's what I just said, is this problem. So just assume I have a system in simple shear, but I'm going to allow this to be a weak region with a low viscosity. Okay? If you just look at the solution of Stokes with variable viscosity, you put it in shear, what's going to happen is the pressure, the dynamic pressure in these regions is going to drop. Okay? To enforce incompressibility, if this is weaker. Okay? But if there's a low pressure here and this is a porous medium, well, then melt's going to flow to move into it. Okay? And if the viscosity itself is porosity weakening, it just gets weaker and the whole thing is unstable and falls apart. Okay. So that's the simplified version. Yes?
So I appreciate that mathematically you can do this without melting, but do the experiments, can you explain from the experiments that your gamma term was 0, or?
I think overall, yes. I mean, you saturate the melt in olivine. It's really only olivines there, and it's easy to saturate. You just leave it there and cook for a while. So I don't believe there's any mass transfer. Now, whether that's true at the grain scale, whether there's local grain scale rearrangement, that's a different question. But in terms of bulk mass transfer, net mass transfer between solid and liquid, I don't believe that's the case. Okay.
I support you.
What?
I support you.
Thank you. And it's right. Okay. So here's my little version of that. Not as pretty as what Rich did, but I just wanted a movie, so I did it myself. So this is the solution of those equations, our basic McKenzie equations for this problem. Run it again. Doesn't work that way.
What are these errors now?
Arrows are the solid velocity field, so it's in simple shear, it's moving fast to the top, it's 0 at the bottom. Okay, I'm just shearing it.
And initial conditions, is it randomly distributed porosity or whatever?
It's basically uniform distributed random white noise on the, not even white, it's uniformly distributed.
Filter at short wavelengths.
No, that's a problem. I just hammered it on the grid points. I just said set random numbers, some small epsilon to the porosity. It doesn't matter. It will grow. These are bigger. These are, I forget what my resolution is here. You can see it starts to blow up at the end, and so you can actually see kind of what the nodal spacing is for this particular calculation. But
You have previous slide with experiment. Is it something like that in experiment in previous?
yeah, that's what the experiments are. You start, well,
Previous, so one more. Here, on the right side.
yeah.
Yeah.
So what do you mean? Initially, it's homogeneous solid plus liquid, no porosity segregation. Well, obviously, there's fluctuations at the grain scale. You shear it, and these things pop out. Okay. And the bottom line is, if you take these equations and set them up and do the same thing, qualitatively, you're going to get the same problem, and it simply comes from the feedback between a porosity weakening solid, okay, and the pressure gradients that are generated from it. The details are trying to actually get things like the angle and the spacing and all that right. That's where it becomes a very hard problem. I'm not sure we really have a solution yet. But anyway, this was my first take. Sorry?
Also the amplitude of your porosity.
Oh, these ones are small. So, but here, these are Rich's from when we did it in 2006. And he doesn't believe this either anymore. He said so. But it's still, the basics are still basically right. So this is the porosity. This is actually the vorticity where these things show up more strongly. The issue, the hard problem, well, the thing that's robust is this very low angle with respect to the shear plane. Okay. And then when we did this in 2006, the only thing we played with was the power law rheology. Okay. And it turned out to get low angles for an isoviscous, for a Newtonian problem, the maximum opening directions of 45 degrees. That would be the fastest growing one. To get the angle down, we ended up using a very high power law, a near plastic, the n equals 6. Okay, I'm not sure that that's justified, but that's how you got them in that case. There's been other work, maybe Rich will talk about it, using much more complicated anisotropic shear viscosities. This came out in JFM relatively recently, and these are lovely. This is the shear experiments, these are the torsion experiments. And again, you see this segregation, but the details are complicated. The basic physics is always the same. A variable viscosity will couple shear to dilation. and however you do it, and if it's porosity weakening, it will suck melt in. Yes?
Is there any saturation in these models, or do the bands just keep growing?
No, that's the problem. That's the other problem. Actually, I think I have, yeah, okay. So let me just summarize the bands, and I'm going to quickly do reactive flow, and then there's much more to do, but let me talk about this. So yeah, that's a problem. There are the problems are in the details. So I think the basic instability is sensible. It just arises from a porosity weakening, shear viscosity, and this coupling of shear to volumetric flow. And as I said, any variable shear viscosity couples incompressible compressible flow. If it's porosity weakening, that can lead to an instability. The devil's in the details. The experiments, this low angle shows up no matter what you do. Most of the models, it's sensitive to the parameters of the model. So there's a robustness in the experiments that's missing in the models. In the real experiments, they're actually finite width, and they don't compact to zero between them, but the calculations do. So in the argument of surface energy, there's something else in there that we're missing in the equations. Yeah?
So Mark, can you make any statement that's localizing into the band?
Right.
Say analytically what the porosity behavior is looking out from the center of the band. Like how rapidly is it localizing? Is it exponentially decaying out from the center of the band? Is it power
Well,
off?
again, because what's living under here are those solitary waves, the structure of pressure things always have that sort of hump shape. They start by looking basically like solitary waves. So the real bands, this is what's interesting, is they have very sharp edges on them.
Right.
They saturate in the middle and they have very sharp edges. So this is, again, I think that's what I'm talking about, the finite width melt bands. Okay.
That's right. That's why because
So
yeah.
this is, again, these are the fine details, but they're important for testing the theory. That's really the point. And these models often compact to zero porosity. The experiments don't. We need to look at, the point is, it depends on the rheology, and there may be missing physics, particularly at the lab scale, like surface energy, which may regularize some of these capillary forces, etc. But the bottom line, which is useful, is that for a complicated problem, we actually have experiments that we can test this theory against. And that's really...
I don't understand how it can compact to zero porosity.
If in those problems, well, if things eventually blow up, you just keep sucking them, as you go, you just keep sucking the melt in more and more. So basically the regions between the bands dry out. I mean, they get to very, very small porosities, effectively zero. Even with a constant bulk viscosity, I mean, even with a porosity-dependent bulk viscosity. The compaction length goes to zero between the bands, and there's nothing to stop it.
It can't go to zero porosity.
Asymptotically. It gets sufficiently small that it might as well be impermeable. It just keeps going. Nothing stabilizes it.
That I completely, yeah.
Okay.
That I can understand. I can't understand how it goes to zero.
You're saying in
Well,
between.
in the codes, they go to zero and everything goes to hell. Yes.
Numerically, we've got a problem.
Sorry, Dave.
No, you're saying it's between the bands that the porosity.
Yes, between the bands. Yeah, okay.
So in the experiments, you showed that there are horizontal bands. Were you able to reproduce those?
Well, wait a minute, let me just quickly go back. Which ones do you mean? Like, oh, these things here?
No, the slide before where you showed yes, here.
Where?
The torsion experiment.
Oh, no, you got to be careful. This is a thin section across a chord. So they're all at angles, but they're oriented around the torsion. So this is radius further out. This is going a little bit in. So this sort of sigmoidal shape. But I mean, you did these in torsion.
Second.
No, that's a radial section.
That's a radial section. So you're just looking at a slice, but they're dipping.
Even on the left side, you see very low angle
Yeah.
bands, and you see slightly higher angle.
Well, you see actually all kinds of stuff in here that the details are. These don't. If you really care, they don't. The models don't do that. Yeah, I'll let you.
The different angles, they do a little bit. I mean,
Yeah,
I'm
well,
not saying
Yeah.
it's all answered, but
Well, what's actually weird is if you watch these, they're not because these bands are actually advecting in time through these calculations. They look like they're linking up, but they're actually always moving relatively. They're actually growing local segments that are unstable, and those things are connecting. It's a little bit more complicated as to what's actually going on. But I'm out of time. Do you want to do reaction? Can I?
Yeah, you've got
All right.
my fault the other way.
Yeah, it's your fault, but I hate to break into coffee. That would be cruel. But all right, let me finish off here. I think I said all that. All right, so I want to talk about one last coupled problem because it came up a lot in discussion yesterday, which are these reactive channels. Okay, and that's a different form of coupling. And again, it was driven The last one was driven by experiment. This one's driven by observation. We've seen this picture many times. This is, again, a section of the upper mantle in Oman. The dark bands are Hartsbergite. They're basically olivine plus orthopyroxene. And these light bands are dunite. The orthopyroxene is gone. And that's Kellerman. That's Hirth. I should have added him, too. Man's insane. And he really pushed a lot of these ideas. And his original idea was that what you're looking at here is these are the relics of reaction channels where melt has moved through. Orthopyroxene is not in equilibrium. Sorry, they're sideways because the whole system has been transposed. But the notion is that when these were being formed, they were vertical. Okay. But that melt has moved through here and has reactively dissolved out the orthopyroxene, leaving a dunite residue. There's lots of evidence for that, but one of the interesting ones is a chemical argument, which is if you look at the composition of small pyroxenes that are relic in the Hartsbergite, the rare earth patterns are extremely depleted. These things look like abyssal periddotites. But the ones in the dunites and how they survive, I have no idea, actually look much more like the melts that go through there. So these things have equilibrated with a melt that looks something like Morb. This stuff is extremely depleted. Okay. And the other argument, the big one that drives it all, is that Morb is undersaturated in orthopyroxene. So it could not be in equilibrium with that material, or it would have been saturated. Okay. So that's what drove the ideas. And really, this is really Peter's idea, but I'm a better modeler, so and they not. So anyway, we said, okay, can we set this up? We have a set of equations. Can we model a simple model of reactive infiltration for this problem? And so here's the model setup I'm going to describe. It's sort of a variation on, so the original paper was myself and Peter, 95. These calculations were in 2001 for a slightly different problem, but I'll just set this up. Here's the idea. I'm going to have a static, nominally static solid. I'm going to flux it with a reactive melt. I'm not going to allow any reaction in the bottom just to sort of keep things away from that bottom boundary condition. But I'm going to have a reactive zone. And the reaction that's going to go on in here is a very simplified dissolution reaction trying to mimic that orthopyroxene dissolution. And so what I'm going to assume is, so here's our phase diagram as far as it is. Sorry, this blue line is the initial concentration of the soluble phase. So there's a soluble phase and an insoluble phase. I'm going to start with about 50% soluble phase in here. Okay. But that phase is in equilibrium. That phase has a concentration in the liquid, which is that green line. That's the equilibrium concentration. So if it was just static and in equilibrium, the solid, well, it would have whatever solid it wants. This is actually approximating a paratectic system. You'll notice that the amount of this material in the fluid is actually greater than 1. That's effectively paratectic. The important part here is that there's a gradient in solubility that, and this is true of pyroxene, that as you decrease pressure, pyroxene becomes more and more soluble in the liquid. So now you have this gradient in the solubility field. And so what happens is very simple. I'm going to have a porous material moving through here that's trying to react with this thing. Any advection is going to move me away from equilibrium. I'm going to take that profile and I'm just going to shift it upwards. But now I've moved off of equilibrium. Okay. If it's reactive, to get back into equilibrium, I have to dissolve some of this material, okay, and add something else, and this is the critical thing. You have to add something else to it to pull it back into equilibrium. Now, for this particular calculation, I'm going to do a sort of stupid thing, but it was hidden in some of my earlier work, is I'm going to assume that the thing that I add to it is just a constant offset of the equilibrium one. And this offset will turn out to be very important. So not only in reactive flows do you need to know what the equilibrium concentration is, you actually have to know what the reaction is. You have to know what you're adding to it to bring it back to equilibrium. That's what I need to talk to you about. But we'll see how this all works. So that's what it looks like as a diagram. This is what it looks like, a set of equations. It's starting to look ugly, but it's not bad. This is basically, we've thrown away the incompressible flow. This is just the compressible flow equations. The only thing I've added is a melting, a dissolution rate. I'll keep this one in, it doesn't matter. Okay. But the important part is that this mass transfer term I'm going to describe with a simple linear kinetics problem. I'm going to say that the mass transfer depends on, well, dimensionlessly a Damkohler number, but just think of this as a reaction rate times a specific reaction area. Okay. This is in there, which is important, which is if the porosity goes to 0 or there's no soluble phase, it shouldn't react. So this thing vanishes in those two cases. That's the only real property of it. But it depends on the difference between the fluid concentration and its equilibrium concentration. If my fluid is, I think I got my signs wrong. Anyway, it's the difference. And once you do that, then you couple, but here's the point. Once you've chosen this form of a gamma, I now need to track composition. So I have two more conservation equations, one for the transport of the fluid concentration, which looks like this, and one for the evolution of the solid concentration. And the important parameters here are the Dam-Kohler number, which is basically how reactive it is, the reaction time divided by basically how fast you're moving the material through flux. And there's also, I'm allowing a little bit of diffusion in the liquid, and that's controlled by a Peclet number. All right. And the flux is, again, depends on the compaction pressure. The question is, how does this work?
Gamma positive?
Gamma should be positive. I've written that wrong. Yeah. So bottom line, if I'm lower than saturation, I need to melt. I need to dissolve. Sorry, that was a huge error. Put those signs. Okay. So once you've chosen this form of gamma, now I've coupled these equations to this. This is where all the action happens. So this is advection of composition. It says that the change in composition with time depends on, it is coupled to the fluid fluxes, which depend on the mechanics, and the difference between what I'm actually adding the reactive composition to the fluid composition and the rate plus a little bit of diffusion.
CF equilibrium, is that the constant here?
No, that has that gradient in it. That was that green line. Okay. And right. So this is where all the coupling has. Gamma is a function of CF. This is a function of CF. If I'm out of equilibrium, I'm going to drive. Gamma is going to change, but gamma is going to come up here, change the porosity. The porosity is going to change the flux. And what I've done is I've coupled the flux now to the dissolution rate. And what that does is, let's do this right. This is not a recent, this is a new calculation. It just goes gangbusters. Those are flux arrows at the end. It gets this is having a hard time getting out, and so I've generated this very large thing. I wish I could slow that down. Maybe I can. Oops, no, I can't. Run it again. So what you're looking at here, sorry. This is the porosity field. Starts off constant porosity at 1%. This is the solid concentration field. Starts off with a uniform 50% soluble phase plus minus some white noise. And this is the fluid concentration. Oops. Stop. These two things. All right, one more time. So it's reacting. The channels are growing. They're dissolving solid. And you'll notice once they pretty much exhaust the phase and the dissolution turns off and they start actually splitting and dissolving the edges of these things. So the channels move around. The residual, this is not what the channels are. The channels are actually, you can see them around the edges of this thing. Okay. And the important part is that the fluid is actually out of equilibrium. If this was a straight plane, but you can see the fluid channels. It's actually transporting these things not in equilibrium with their regular. So, all right, I better finish up here. Just want to give one little rule of thumb for now, there's been a lot of work. Is Mark Hess? Where's Mark Hess? There you are. Hi. Lots of people have worked on this. Some people get waves. Some people get, there's been a little bit of confusion about when this is important or not to get channels. And I want to try and clarify that a little bit with one last bit, which is that you can understand a lot of what's happening in this problem if you just consider the near equilibrium case. I'm going to take the Dam-Kohler number to infinity, which forces the fluid concentration to go to equilibrium. So the problem is now gamma, our melt term, is infinity times 0, which is actually a bounded number, but the bound comes from this equation. You have to back solve for what the dissolution rate is. And you can see it. If I say CF goes to CF equilibrium, and that's roughly steady state. That drops out. This becomes the gradient of the equilibrium concentration times the melt flux. This becomes the difference between the reactive concentration and the equilibrium concentration. And I'm just going to ignore that one, because it's not that important. So I can then solve for gamma, and it simply becomes, it depends on the flux, the gradient of the solubility. Okay, so if there's no gradient in solubility, it doesn't react. If the steeper the gradient, the more advection pushes you away. But the strength of this term depends on the distance between what you need equilibrium and what you need to add to it to return to it. Okay. In this case, it was 0.1. In my case, I made this thing very strong. If you get a lot of dissolution over a compaction length, you will drive the channels. Okay. If it's weaker than that, you'll get other behavior. And this thing was sort of hiding in some of my code. So I wanted to put it out there. So for this case here, right, so the reaction rate in equilibrium, for large Dam-Kohler number, it's simply the flux times this gradient divided by that distance. Okay. If you're saying I'm going to add something that's way out here, okay, it doesn't take much leverage to get that back into equilibrium. It doesn't do anything. Okay. If I try to add something very close to equilibrium, I get enormous dissolution rates. So you need to know two things. You need to know the equilibrium concentrations and the reactions to do this sort of thing, and that becomes the hard part here. Yeah?
Isn't that one of the issues of applying this to Dunite channel formation, is that we're assuming that's an incongruent reaction which actually places the red line further out to the right, which then takes away...
Well, the green line's out to the right, too. It's incongruent. That's not a problem. The melt has more pyroxene in it. Yeah, if you pull this thing out further, but all I'm saying is this is what affects it. You need to know what the reaction is. If I put it out here, or I put it way out here, then it makes it harder. But it's the amount of dissolution over the compaction length. And this gets back to this question of what's your bulk viscosity, what's your compaction length, and those things can change by orders of magnitude. So it's still, I think, open. I've gone way too far, and you need coffee, I can tell. I need coffee. But have I said anything new? Oh, I didn't show you. Nah. Anyway, I looked at the chemical effects of these things, and we've seen these sort of patterns about small-scale heterogeneity at small scale. One of their interesting features is that if you look at just the trace element response of flow-up of one of these channels well resolved, you actually can generate very large variability in trace element compositions over a very small scale. It doesn't help you with the isotopes at all, but it's interesting that for a homogeneous source, I can generate the kind of fractionations that you seem to see. So channeling may have a chemical effect. I'm not going to go into that. Let's just stop here. This and one more thing. So what did I say? Sorry. The overall equations are a couple multi-physics problem. There's a rich range of behavior. We've got porosity waves, melt bands, reactive flows. I didn't talk about it. There's porosity-driven convection. Okay. But I believe most of this behavior can be understood as various degrees of coupling between these two major modes, an incompressible flow and a compressible flow. Okay. I think this pressure split formulation provides a rather convenient framework for taking these things apart and putting them together again. There's a lot of open questions. I showed you individual mechanisms. There's questions how they interact with, how does reaction interact with the shear bands? How do these small-scale features work at larger scales in the presence of melting or geological settings? Do these small-scale processes influence the large-scale dynamics? Do they change bulk permeability? Do they actually change the flow fields? Most importantly, what are the observable consequences for all this work we go to? Does this thing actually manifest itself in data? And then the part I won't talk about is computation of these, which is there's so many games to play. I think we need a change in the way we do computation in them to make it more transparent what we actually do in these calculations. And we've got some software to do that. I'm not going to talk about that. We're going to go to coffee, unless there's any really pressing questions. But you're in charge. Yeah.
Are there any pressing questions? More important than coffee.
I'll put up a plug. That's the software that does some really cool stuff. All these calculations I did recently are all in this software, Terra Firma, which really stands on the shoulders of giants, but it has some cool features. All right, go. Coffee. Get out of here.